Up to now, most of the equations that we've looked at might take the form something like y equals some function of x. Could be x plus 3, or y equals x squared minus 7x plus 4, or something like that. Occasionally, they might even take a form of x equals y squared minus 7, or something like that. Some other type of function. But there is another kind of equation, and these are called parametric equations. Parametric equations often come about when we can measure the motion of something in one direction and measure the motion of something in another direction, and then we want to link them together. That might sound strange, but let me give you an example. Imagine we had some sort of contraption that was going to launch a ball off a building or a cliff. If this ball is launched at a certain speed, then if we take into account very little other than the fact that it's going at this speed, I can work out that my direction in the x direction will be some function of time after the ball is released. I can also consider gravity, and therefore consider that the position of the ball is going to be some function of time in the y direction. Now, if I know the way gravity works, and I know the speed that the ball is released going across, and assume it doesn't change, then I can work out my equation with y and x according to where the ball is at any point in time. This is what a parametric equation is. The extra parameter here is this idea of time. So what will often happen in this unit is we'll be given the movement or the way something happens with regards to time, and we will try and remove time from the equations so that we can look at how this body moves in the x and y direction. We'll link them up somehow. So here's an example of what might happen. We might know, given this, that my ball is released at 5 meters per second. So every second the ball travels another 5 meters in the positive direction of the x-axis. That would assume the edge of the building is my y-axis. We might also be aware that as the ball moves, it accelerates at a certain speed, or accelerates at a certain rate towards the ground. So there'll be some function of time. Now, whatever this equation is, what we can do is we can then look at my t and we can make a substitution. For example, here, t would be x over 5. So wherever I see t in this equation, I can substitute x over 5. And therefore, at the end of this whole exercise, I'm going to get some equation that talks about y as a function of x. This is the whole idea of parametric equations, that when we can measure one direction in terms of time and another direction in terms of time, we can then combine our two directions and have a look at the motion independently of time. These parametric equations can talk about all sorts of motion or all sorts of equations. We can talk about linear or parabolic equations. And in this circumstance, quite often x will be something like, let's imagine, t plus 2, and y might be t squared plus 7. When we rearrange this equation, we can substitute this into the equation for y and get some kind of y as a function of x. But we can also manage other types of equations. We can manage circles, we can manage ellipses, we can manage hyperbolas. And there are specific equations that we use when we manage these. For example, the Cartesian equation for a circle might be something like x squared plus y squared is the radius squared. That would be the Cartesian equation for a circle that's centered at the origin and has a radius r. However, if I wanted to express a circle in parametric equations where t is my variable, I might find that x equals r cos of t and y equals r sine of t. By using these, I can make substitutions and then transfer between parametric and Cartesian equations. Similarly, I can do something like that with ellipses. For an ellipse, the Cartesian equation might be something like x squared over a squared plus y squared over b squared equals 1. In this circumstance, the x and the y are my coordinates, and a and b give you an indication of where the intercepts are. This ellipse would be centered again on the origin. The corresponding parametric equations will be something like x equals a cos t and y equals b sine t. They're similar equations to the circle, but you'll notice my a and b appear as the a and the b here. Remember, in both the case of the circle and the ellipse, x and cos have a relationship, and y and sine have a relationship. Similarly, for a hyperbola, we have both parametric and Cartesian equations. My Cartesian equation for a hyperbola that's centered on the origin might be x squared over a squared minus y squared over b squared equals 1. The appropriate parametric equation is x equals a sec t. Remember, sec is one of these reciprocal functions, 1 over cos, y equals b tan of t. These again, just like for my circles and for my ellipses, are interchangeable, so we can move between Cartesian equations and between parametric equations. In all of these situations, you can see that your parametric equations use circular or trigonometric relationships. Remember though, that for each of these, there are established relationships where some type of arrangement will allow these to equal 1, such as sine squared t plus cos squared t equals 1. If you can investigate the relationship between those and between secant and tan, that will open the door into an opportunity to convert between parametric equations and Cartesian equations every time. If you found this or any of my other videos helpful, please subscribe to my channel or like the video. Thanks.